Hi. Also welcome from my side. So now we'll be completely switching gears and looking at, as advertised, compute time. Namely, in the next few slides, I would like to first introduce you a little bit to the HPC resources that we have here in Paderborn. We're one of the 9 NHR centers. So NHR stands for Nationales Hochleistungsrechnen, so National High Performance Computing. There's a alliance of 9 HPC centers. We are one of them, and we are focusing on physics, chemistry, computational chemistry aspects. So let me get started with like 2 little bit advertisement slides for our HPC systems. They're a little bit spec heavy, but probably you guys have an idea of what to look at, mainly, for example, GPUs. So this system here, Otus, is our new flagship, new system. It was just brought into operation beginning of September this year, so just about a month ago. It's a combination of normal compute nodes with the newest bleeding edge AMD Turin CPUs, a lot of main memory for quantum chemistry applications, GPUs for molecular dynamics, and nowadays also AI, and planned also FPGAs for other scientific applications. So if you're interested in the specs, have a look. Under this link, you can also find more extended specification of the system. If you're interested in using it, please stay tuned for one of the slides where I also tell you a little bit about how you can use our systems later for research. The system that you're going to be using for the tutorials is Noctua 2. Noctua 2 was inaugurated in 2022, so already has been in operation for some time. And since we wanted to have a well-tested system for the tutorial, we choose Noctua 2 for the tutorial so that nothing can go wrong. With Otus, it's still a little bit new and still in testing phase, so we didn't want to risk it. So you'll be using Noctua 2 during the tutorial. It's also an AMD-based system, basically a generation older than Otus. Also has a number of different nodes with different sizes of memory. For example, here also huge memory nodes with up to 2 terabytes for quantum chemistry simulations, or most importantly for you later, here the GPU nodes with A100s, NVIDIA A100 GPUs that you will later be using for example, GROMACS simulations. If any of these 2 systems has sparked your interest, I would like to give you a very short overview on how you can access those systems. So our HPC systems are usable for academic users, Fachhochschulen and HAWs in Germany. So if you're a member of a university in Germany, you can go ahead and apply for access to our systems. And there are 3 main access routes. The NHR starter, which is the easiest one. So you get here up to, for example, 8 million CPU core hours per year and up to 10,000 GPU hours per year. But you only have to fill out a very, very short online form, and within a few days you get access. If you need more resources, then we have project categories like NHR normal, up to 30 million CPU core hours and 100,000 GPU hours per year, and then NHR large, which is everything beyond 30 million CPU core hours and 100,000 GPU hours. Due to this NHR normal and NHR large being sizable compute resources, we unfortunately, due to the funding regulations, you have to write up a proposal, but there are a number of simplifications that you can do. For example, if you already have a scientifically reviewed project, like a DFG project or a project from the European Union, then the proposal for getting compute time is a lot easier. If you have any interest in that, please let us know during the tutorials. We can talk about details, and you can find all the information here on our webpage. And feel free to, or don't hesitate to ask us any case. So now let's come to how you will use our HPC systems in practice during the tutorial, which will start just after the coffee break today. So you'll be using our HPC system via our so-called JupyterHub. JupyterHub is a a software that lets you use your web browser to access the HPC system, for example, for Jupyter notebooks, for terminal session, for remote desktop, and these are exactly the features that we're going to use today. So here under this link, jupyterhub.pc2.unipaderborn.de, with the login information that you got via email, probably last Friday, you can log in and then start your own JupyterHub server instance. In this server instance, you ask for a preset. We have configured a preset here for our autumn school, so the CP2K GROMACS autumn school. Then you start it, and then the environment is set up so that everything is already there, what you are going to use. And what you're going to use is, on the one hand, here in this launcher, a notebook. That's a typical Jupyter notebook for the tutorials. But we also have the possibility here to use a remote desktop, which means that on the HPC system, so basically on the HPC system, a desktop is started and the picture is forwarded to your laptop so that you also can start graphical applications like you can see here. So that's a screenshot of the remote desktop. And if you, for example, want to use VMD applications, even a web browser or other graphical applications, you can simply do that. That all runs is transmitted to you, to your web browser, and you don't need any additional software installed on your laptop to do the tutorials, which makes it really easy and hopefully unproblematic to access the HPC systems and use the resources. So, talking about HPC resources. So you know from our earlier slides that we have about Noctua 2, 1,100 compute nodes, or in Otus, about 750 compute nodes. Maybe can I see a show of hands who has already used an HPC system in practice? Okay, nearly everyone, so I'll keep it short. If you have any kind of questions, please ask during the tutorial. The important thing that you need to know about an HPC system is that you don't just go to the compute nodes themselves, but in between we have a so-called workload manager. In our case, that's SLURM as a workload manager. And what you do is you formulate your compute job with a so-called job script, which is basically just a bash script, which then describes what your compute job is supposed to do, which kind of resources it's supposed to use, for example, how many GPUs. And then you submit this compute job to the workload manager, and sometime later, when one of the compute nodes or the number of compute nodes that you requested are free, this bash script is executed there and writes all your result files to the parallel file system that is connected to all those compute nodes. When you specify such a job script, there are a number of parameters. Here are a few examples that might be interesting. For example, you can give this job a job name with -j, minus job name. You can specify compute, or need to specify compute project, which in this case is the compute project for this, this autumn school. And on our system, it's mandatory to specify a maximum job runtime, which, for example, here is 30 minutes. And here's just an example of a time format. So usually for the calculations you'll be doing here, several minutes should be sufficient. And that's the maximum runtime that a job can run. Then it will be automatically stopped. In addition, you want to specify what kind of hardware in terms of CPU cores and GPUs you're using in a job. There you have the argument for the partition, -p. So in our case, as you've seen here on the first slide, you have the partition names. Straightforwardly, if you just want to use CPU, you'll be using the normal partition. And if you want to use one of our GPUs, then you'll be using the GPU partition. Okay, so specifying the partition, then the number of compute nodes, n-1 means a single node job, then the number of tasks, which in MPI, or for an MPI parallelized application, means the number of MPI ranks. For example, here 4 MPI ranks. And then last but not least, the number of CPU cores per task, which is threads, OpenMP threads, for example, are supposed to be used for one per MPI rank. So in this case, this would spawn 4 MPI ranks, n equals 4. And for each MPI rank, it would be using 16 CPU cores. So in total, 64 CPU cores. For using GPUs, as I already mentioned, you will be using the partition GPU. And then you have to specify how many GPUs you want to use in the job. This GRES specification here is necessary, where you specify GRES equals GPU, A100, and then the number of GPUs, for example here, a single GPU. In our nodes, we have at most 4 GPUs in this configuration. They're interconnected with high-speed NVLink connections. So you could also run multi-GPU jobs here with up to 4 GPUs per node. For benchmarking purposes, it can sometimes be helpful to exclude other users from running jobs at the same time on the node, for example, using the other CPU cores that are still available. For that, you can use the flag exclusive to make sure that you're the only person on this compute node at a time. But in normal usage, that should be avoided because you're potentially wasting the resources. If you're now asking about how can I get access to software, and there we have quite a vast repository of pre-installed software. Here's an example for GROMACS. You can see a number of GROMACS versions compiled with different compilers, with or without GPU acceleration. And we have this small, nice tool, find module. And you can, for example, write find underscore module, and then some part of the name of the program that you're using. For example, here CP2K, intentionally written in a rather weird way to show that this search is case insensitive, and you can also put in just a partial or incomplete name, and then it will find every module where CP2K shows up in the name, which makes it a lot easier to find a module and all the available modules for the software.
Excuse me, available module or a spider doesn't work right?
In principle, it works, but this find module is a lot more convenient. So we are running a hierarchical naming format, which you can see here with bio and then GROMACS and then the versions. And usually, if you do module available, so module AV, you will only see these meta modules like bio, chem, phys, and so on, to keep it nice and organized. And that sometimes breaks module spider because it can't directly see it. That's the reason why we have this find module, which then automatically crawls into all the meta modules and the whole. Okay, so for example, for GROMACS here, you can see the list. Also on our documentation here, you can find software is documented with usage examples and additional hints on how to use it on the different systems. If you now write a job script, of course, you need to load such a module file. For example, here, bio GROMACS 2025.3 with GPU, which is indicated here by CUDA at the end. We recommend to use module reset before that in the job script. Module reset resets all the loaded modules, gives you a clean slate, and then you load a module, and everything is nicely well-defined, and nothing from your previous environment is still leaking into it, and this can avoid problems in the future. So that overall, an example job script that you could use on our systems looks like the following. So we have the bin bash as usual. Then we have here this block where we instruct SLURM on how to allocate a job, for example, using the compute project HPC PRF IASC PGR, which is the one for this autumn school, using one node, using one rank, using 16 CPUs per task, so per rank, setting a maximum job runtime of 2 hours, instructing it to use the GPU partition, and requesting 1 GPU. Then we just, for everything being nice, reset the module environment and load the GROMACS module, set some, this line is actually optional, some OpenMP threading parameters, and then as run GROMACS with GPUs here as an example. Once you've submitted a job with SBatch and the job script, you also would want to control it and see if it's running, what the state is in. For that, you can use SQ to show which jobs you've currently started, if they're pending, if they're currently running, or if they've completed. If you want to look into details of a job, there's scontrol show job, and then the job ID. If you want to cancel a job while it is running or while it's still pending to be executed, use scancel. And the default output file of the standard output of a running job is slurm-jobid.out in the directory where you've submitted the job. For GPU usage, it's usually a good idea to check if the GPU is used properly, because GPUs are rather expensive resources, and then it's important to check that the code is actually using the GPU when you've started it, and that it's also being used to sufficient extent. And for that, we recommend to, especially when you first submitted a job, check the job at runtime. You can do that by first finding out which node. You would do that by running SQ. You get this output, and here you can see that my user, Schade, is currently running one job with this job ID on the GPU partition in the state running, so it's currently being executed, has been running for about 4 seconds on one node, and the node that's running is N2 GPU 1211. Then, once you have a job running on a compute node on our systems, you can SSH to the node, so log into the node, and then on the node you can directly run NVIDIA SMI, which is a tool to investigate the GPU usage and to get some other statistics parameters from the GPUs. In this case, since this job has allocated one GPU, you will only be seeing one GPU here, an NVIDIA A100. In use are about 39 gigabytes of the available 40 gigabytes in the GPU. Currently one process, in this case a LAMPS example, is using the GPU. And one very important number here is the GPU utilization, which should, if possible, be beyond 80 or beyond 90%. If you have a very small GPU utilization of 0 or something below 40% or so, you should look into your job allocation to make sure that your application is using the GPU in a suitable way, because otherwise you're wasting these expensive GPU resources. In addition to this live checking of a compute job, we also offer an after-the-fact checking or to get an idea of how your compute jobs ran. For that, we have our so-called job monitoring system called Cluster Cockpit. You can find that here under this URL, where you would log into with your credentials that you got via email, and then you see a list of your compute jobs together with a number of metrics that were automatically recorded while the job was running. For example, floating point throughput of the CPUs, also the GPU utilization, and a number of additional metrics that can give you very valuable insights when you want to tune the performance of your compute job or want to see where certain bottlenecks are during the execution of this compute job. Here's an example. On the top, you will see meta information of your job, then a so-called roofline model, and here the individual statistics. And let's see if we can pick out something interesting. For example, here, flops any is the floating point throughput of the allocated CPU cores, and you see some interesting spikes here of some of the CPU, some of the nodes in the job. These statistics depend on the workload that you're running and the compute node that you're running on, but they are a very nice way of checking after the fact. For example, when the job has already stopped, for example, how your GPU utilization during the whole runtime of the job was. I want to conclude with a short cheat sheet for our system. So, as I mentioned, we are running SLURM as a workload manager. You can use the nodes either shared or exclusive. we have 128 CPU cores per node in Noctua 2. Memory per node is between 256 for the normal partition, up to 2 terabytes for the huge mem partition. Here's a list of the commonly used S-batch parameters, like here the account, job name, time, together with here an example of a job script, and then the mentioned small tools like S-control, S-cancel, or SQ to control your jobs or to investigate or check if they're running, if they're submitted, or what their status is. And that is already from my side. I hope I stayed in the time. Yes, exactly. So at 15:30, we wanted to go into the coffee break. But before we go, are there right now questions? Otherwise, we'll be available also, of course, for technical questions and problems during the tutorials. Okay, then I guess everybody's waiting for the coffee break. And see you guys later.